Hello everyone, so we're going to dive into electron configuration and quantum numbers. In the last lecture we talked about doing orbital notation with arrows, so we're going to review that again really quick. So pause the video and do magnesium and then do chlorine, and then we're going to go back and check it. Okay, with magnesium, or with any element really, remember the first thing you have to do is to find out how many electrons there are in the first place. And so with magnesium, right, there are 12 protons, so because it's neutral, there will be 12 electrons. So we have let me plug in my little tablet that lets me take notes. You have 12 magnesium. 12 electrons in magnesium, rather. 12 electrons. And so, remember you have the 1s orbital, 2s orbital, then you go 2p, and you have 3p orbitals. And then you would go up to 3s. And so you have you have to fill in the first level before you can go to the second level. We have to fill up all those before we can go to p. And remember, once you get to orbitals that have more than one, you have 3p orbitals, you have to fill those up one at a time. 1, 2, 3. And so I'm going to kind of just keep track. I have 2 done, I have 4 done, 5, 6, 7, 8, 9, 10, 11, 12. Okay? And so with chlorine, let's check to see how many electrons we have. We have 17, because we have 17 protons, and we're talking about neutral chlorine. And so we're going to do the arrow notation for 17 electrons. Okay? And so it goes off with 1s, 2s, 2p, 3s, and 3p. I don't think we're going to get to 4s, but I'm going to write it just so you can kind of get the pattern. And so we have 17 electrons, and so we fill up the 1s, the 2s, the 2p's one at a time. So here I have 2, 4, 5, 6, 7, 8, 9, 10, right? So I have 10 so far. I have to fill up 3s before I can get to 3p, so that's 12. 13, 14, 15, 16, 17. So we haven't used that 4s. So let's erase that real quick. Alright. And so counting the number of errors that you have helps you keep, and if you don't have the right number of errors, then you know you need to go back and redo your problem. So 14, 16, and then this is 17. And so let's check our answer. Okay. And remember, we touched on a little bit in our last lecture how we're going to go from this to this, and so pretty much this is 1s2, right, because this is filled, 2s2, 2p, 6, because it's 2, 4, 6, and 3s2. Then you have 1s2, 2s2, 2p, 6, 3s2, and 2p, 1, 2, 3, 4, and 5. Okay? And so this next link is a video on how to use the periodic table to determine electron configuration, so that way we don't have to draw this out every single time to be able to go from here to what we have here. Okay? Some people like to memorize it, to memorize this pattern here all the way through up to F. If you're good at memorizing, then go with that. If you're not good at memorizing, I'm not good at memorizing anything. I forget my own dog's name at times, and so the periodic table method is really good if you want to be able to figure out these problems to get a good grade, but in general just know how to figure out these problems without having to do a bunch of memorizing. And so just briefly, this video goes into how the periodic table is broken down such that you can figure out the electron configuration from how the periodic table is set up. And so You have your S block, your D block, your P block, so it'd be S, and this helium goes with one S. So helium goes with one S. Okay, this one right here. Otherwise, though, the pattern is pretty accurate as far as how they illustrated it. You have 2S, and so this would be S1, S2. And this would be P1, P2, P3, P4, P5, and P6. So the way this would work is this element, whatever it is, its last, the last part of that electron configuration for this element would be 6p6. Okay, and then you get to D, so you get to D1 and D2, D3, D4, D5, D6, D7, D8, D9, and D10. Oops, D10. And same thing for F. You would have F1 all the way up to, why did I write 4? It's supposed to be F. You'd have F1 all the way up to F14. Okay? And so you would use this pattern to write out the entire electron configuration. And so we're going to do an example. We're going to walk through an example, which is what this regular periodic table is for, to help us do this example. Oh, also you'll notice, just a note, that you're going to go from 4s down to 3d back up to 4p. And it's weird like that because the 4s has less energy than 3d. So you're going to go from 4 to 3 to 4. And really the rule is when you get to the D block, you subtract 1. So really what you're going to do is you have the row number, right? You have 1, 2, 3, 4, 5, 6, 7. Whatever this number is here, when you get to the D block, when you get to the D block, subtract 1 from the row number. Alright, so if you're in 7, you go to 7s, you do 6d because you're subtracting 1 from that row number. And we'll practice it here in just a second. And so we're actually going to do the first one that goes into that D block, scandium, which is number 21, which is here. Right? And so you're going to go and you're going to do, this is going to be 1s1, right? And this will be 1s2. Then you're going to have, then you're going to go through here, so then you'll have 2s2. And then you'll have 2p6. Then you'll have 3s2, 3p6, 4s2, and when you get here, it's going to be 3d1. And I know this is broken up kind of weird right here. I'm not sure. Well, I guess they do that because these fit in here. But anyways, when you go here, scandium would be here, where you would have 3d1. Okay? And that's how we got to 3d1 here. And so if we're writing it all out for scandium, okay, we're going to go 1s2, 2s2. We went through the p's, 2p6, 3s2, 3p6, 4s2. And you would usually have like your periodic table right next to you, so you don't have to remember it. You can write it from here. 4s2, and then that last one's going to be 3d1. Okay? And so now we're going to do arsenic. I'm going to write that, transcribe that here. 1s2, 2s2, 2p6, oops, 2, 2p6, 3s2, 3p6, 4s2, 3d1. Remember, we subtracted that 1 from here. Okay? And so, we're going to do arsenic. So let me erase this stuff. And maybe, just so you can try it, you can go through the video or you can pause this video and you can try it yourself, and then we'll go over it. Okay. And so number 33, arsenic, is here, right? And so we're going to go through 1s2, right? We're going through here. That's going to be 2s2 because we're going through here. 2p6 because we're going all the way through here. 3s2, 3p6, 4s2, 4s2, and then we are here at the D's. This is the D block. Let me write that. D block. So then it's going to be 3d10. Then we're going to get back into the P's. So that's 3p1, 3p2, 3p3. Okay. So we did 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then we went back up to 4. Oop, and you see my mistake there? I stayed in the 3's. I should have went back up to 4. So it should be 4p1, 4p2, 4p3. So when you get through here, make sure you add that one back in there. So we're at 4p3. 4p3. And so you're kind of, sort of, hopefully seeing a pattern here. And this can get rather long and lengthy, especially when you get down into F. It can get a little bit tedious. And so there's also a shorthand. Once you kind of get this configuration figured out, there's a bit of a shorthand way of doing things. And so we haven't gone over the parts of the periodic table yet. We will in our next lecture, but just know, and some of you may already know from taking chemistry before or any type of physical science class before, these are your noble gases, right? And noble gases are very stable because they have 8 electrons in their outer shell, and we'll talk about that later, except for helium. But helium is also very stable because that first shell can only hold 2 electrons, as we know. And so it's happy as well. And so because the noble gases are very stable, we can use the noble gas to do what's called noble gas notation. Where you start off with the closest noble gas that was previous to it. So for example, if we were doing chlorine, we couldn't do argon because it has too many electrons. We'd have to go with the closest one that was previous, which is neon. Okay, and so if we were going to go back to chlorine, to our example here, right, we can shorten this up a little bit by just starting off with neon in parentheses, right, or I'll just do it here. So for chlorine, we can do neon, right, we start with neon, and then we can go straight to here, and this is the 3rd row, so we would go 3s2, write that here, 3s2, 3p1, 3p2, 3p3, 3p4, and 3p5. So 3p5. And so we would do neon. Alright, neon would be, let's go back here. Alright, we start off at 3s2. So this would all be, oh, you see I made a mistake here too. I didn't put 3s2. It is very late and I am not caffeinated. I apologize. 3s2, 3p5. And all this, neon represents all of this. Okay? So we can say neon 3s2, 3p5. Okay? And so that is called noble gas notation. And so if we did this for magnesium, right, for magnesium, magnesium is what we're trying to do, right? And so the noble gas that was most previous again was neon, right? And so I could do magnesium, and then it would be neon. And then it would be, we're at the third row again, so we'd have 3s1, 3s2. And that would be noble gas notation for neon. So, noble gas notation kind of shortened things up again a bit. Let's do noble, pause the video, and try noble gas notation for scandium and arsenic, and we will go over it. Okay, and so if I'm going to do scandium, right, I'm going to go here. This is where I'm at. And what was the noble gas that was previous? Well, that's argon, right? And so I put in brackets argon, and then I can do, that was, now we're in the fourth row, so it'd be 4s2, right, 4s2, 3d1. So 4s2, 3d1. Alright, and I'll do that in a different color. Right, this all represents argon. Then you have 4s2, 3d1. Okay? And so let's try arsenic. Alright, arsenic is here. Right? And so what was the noble gas that was previous? The noble gas that was previous, again, is argon. Right? So we're going to do argon, and then we're going to do, now we're at 4, right? So then it's going to be 4s2. We go through here. Remember, we go down to 3d10. Then we're going to go up to 4. Remember, go back up to 4. Don't do the mistake that I did. 4p1, 4p2, 4p3. And so argon's going to be 4s, or not argon, arsenic's going to be argon, 4s2, 3d10, 4p3. Okay. So, what was the symbol for arsenic? AS. Okay. AS is going to be AR, right? With all this. Then you have 4s2, 3d10, 4p3. Again, this is noble gas notation. Noble gas notation. Noble gas notation. Okay? And so, arsenic, you're going to have, I'm going to do the noble gas notation for this one. Arsenic is going to be, well, I'll write them both out. You're going to have 1s2 all the way up to 3p3, so it's going to be 1s2, 2s2, and writing them out's redundant, but it really helps you to review that pattern. 2p6, 3s2, 3p6, 4s2, 3d10, and then you're going to have 4p3. And this all represents argon. And I know that just from looking at this without looking at the periodic table, because you'll notice here that any noble gas is going to end with P6. So any noble gas ends with, or I'll say all noble gases end with not necessarily 6p6, but with P6. And that's how I can tell when I go from the long hand, right? Because this is going to be the long hand. When I go from the long hand to the short hand, whatever ends in 3p6, or in p6 rather, that is where the highest one with p6, or with your p orbitals completed, that's what's going to be your noble gas. Okay? And so you're going to have arsenic being argon, and then 4s2, 3d10, 4p3. Okay? So that is noble gas notation. Okay? And if you would like to have some more practice for someone to really walk through step by step that D block of subtracting that 1 from that row number and then going back to the original row number, when you go back to that P block, I highly suggest that you walk through this video. Okay? So we've been talking a lot about electrons, and remember when we had this beautiful, very artistic diagram, and I was talking about shells, right? And this is your nucleus. Can't spell nucleus, but your protons and your neutrons, and then you have these shells. And recall that shells indicate energy. Alright, and it was orbitals that indicated location. Alright, so quantum numbers help identify both energy and location. And I should say probable location, because remember, we don't know for certain where any electron is. We don't have the science to know that yet. But it's the most likely place where it is, both energy and location. Okay? And so we have 4 quantum numbers. Okay? And quantum numbers, certain quantum numbers indicate certain things in regard to electrons. And so the principal quantum number is that row on the periodic table, or the shell, rather, I should say the shell, that it's found in. So if it's found here, then that means your principal quantum number is 1. If it's found here, your principal quantum number is 2, and so on. And so the principal quantum number tells us the shell. Right? And so if I had 2p5, this 2 would be the principal quantum number. Okay. Angular quantum number tells us the subshell. Magnetic quantum number tells us the specific orbital within that subshell. electron spin number just tells us if the spin is up or down. So remember when we did these arrows, remember you draw them like if we're doing the p orbitals, up, 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 and then you go through and you do the down arrows. Some people draw them down first and then do it up. In a way, it doesn't matter, but just for convention and just to make things consistent across the board, particularly if you watch videos, most videos are going to have people drawing them up first and then going through and drawing them down. So that just kind of makes things a little bit more consistent and easier to understand, particularly when you're looking at other tutorials. So we're going to go through these individually, and then we're going to bring it all together with some examples. So principal quantum number, like I said, indicates the energy shell. Can be whole integers from 1 to 4. This is important. Cannot be a 0 or a negative number because you don't have negative energy shells and we don't have 0 energy shells. It's a whole number from 1 to 4. Okay? And principal quantum number is denoted by the letter N. Okay? So N, it can equal 1, N can equal 2, N can equal 3, and N can equal 4. N can never be 0, and N can never be a negative number. Okay? Alright, so we are moving on to angular momentum number. So our principal quantum number represented the original shell that we're in, and the angular momentum number goes a little bit deeper and talks about the subshell, and it is denoted by the letter L. Usually, you'll see it look like this, well, like this, but I'm sure there's a way to type in a cursive L on the computer. I'm not that smart. But it's denoted by the letter L, and it can be 0, 1, 2, or 3. And the subshell is dependent upon the energy level that subshell is found in. And so we know that there is an S subshell. We know that there is a P subshell that contains specific orbitals, 3p orbitals. We know that there's a D subshell that contains 5d orbitals. So this contains 1 orbital. This contains 3 orbitals. This contains 5 orbitals. And F subshell contains 7 f orbitals. Okay? So I'm going to try to draw this. So our S looks like a sphere, right? Our S looks like a sphere. Our P looks like a dumbbell, right? And D, let me try that again. That looks terrible. D kind of sort of looks like this. And F kind of looks like the dumbbell with a donut in the middle, which I'm going to try my best to draw. Okay, and so when our principal quantum number, or N, equals 1, okay, L would be 0, okay, and then when N equals 2, L can be, when we're at our first energy cell, you're going to have only S. So let me see about writing this. You're going to have S, right? And when we get to that second energy cell, we can have S and P. And so then S and P subshells, rather. So then you can have L can be 0 and L can be 1 because you have S and P. S and P. And then when your principal quantum number or your energy shell is 3, right? L can be 0, 1, or 2 because now you can have S, P, and D, right? And then when n equals 3, or n equals 4 rather, L can be 0, 1, 2, or 3 because then you have S, P, D, and F. And so we have our principal quantum number, all right, and this is our angular momentum numbers that are possibilities, and it depends on where that last orbital lands as to what L is, and we'll go through that. And so when I also want to point out, when n equals 1, you're going to have 1s. When n equals 2, you're going to have 2s, 2p. Then n equals 3, 3s, 3p, 3d. And then you're going to have 4s, 4p, 4d, and 4f. Okay? And so this indicates what shell you're in. And so, you know, when you have, this is how you get 4p3, for example. This is where that is coming from. And this is just a typed out version of this without all the chicken scratch pictures. Okay. And so when we talk about, when we move forward to the magnetic quantum number, we are talking about describing specific orbitals within a subshell, and that would be denoted by M sub L. All right, and so I'm going to draw this out again. Okay, and so when you have n equals 1, n equals 2, n equals 3, and n equals 4, your angular momentum is 0. It can be 0, 1. It can be 0, 1, 2. And it can be 0, 1, 2, and 3. Okay. And now when we hit to M sub L, right, can be, so the idea is it can be from negative L to positive L. That's the formula. There's formulas to find all these numbers. I don't like using the formulas. I kind of like to use reasoning because I'm bad at memorization. If you want to look up those formulas, there's plenty of videos on it. But this can be negative 0 to positive 0. We know that doesn't really exist. It's just 0, right? It's just 0. And then when we have M sub L, right, we can go from negative 1 to positive 1, right? And so what I'm going to write out are all my options. So you're going to have the possibilities of negative 1, 0, and 1, right? And then M sub L, what do you think it would be for here? Just pause and think about it for a second. For here, your options would be negative 2, negative 1, 0, 1, and 2. And for here, pause and think about what your range would be. What would this range be? What if we keep following the pattern? It's going to be negative 3, negative 2, negative 1, 0, 1, 2, and 3. Okay? And so I also want to point out this pattern that, remember for here we have S, S and P, S, P, and then we can get into D, and then S, P, D, and F, right? And so here we have S, and so S can hold, has one orbital, right? S has one orbital. P is the subshell we're talking about here, and P has 3 orbitals, and we have 3 options for what P can be. D has 5 orbitals, and we have 5 options for where D can be, that orbital where that lands. And then here, remember, F has 7 orbitals, so you have 7 options here for what the magnetic quantum number can be. And so as you write your notes and as you work through these problems, just observe these patterns. As the more you observe these patterns, the less you'll have to memorize, and the more you'll start recognizing how things kind of fit together. Okay. An electron spin number just means a positive 1/2 for an upward spin and a negative 1/2 for a downward spin. And it should be noted that no 2 electrons within the same orbital can have the same spin. So remember when we did, as we were doing arrow notation, right? If I have one S, right, I can't do like this. This is a no. We have one S, it has to be one up and one down. So this would be positive 1/2, and this one would be negative 1/2. Positive 1/2, negative 1/2. Okay? And so let's ask how all this is going to come together. So let's do an example and walk through it and see how all these things come together into doing a problem. And so when you have 2p5, for example, that would be the last electron configuration notation. Okay? And so when you have 2p5, this is your principal quantum number. So n equals 2. And also there's a little trick that you can do. You can write out kind of on the side of your paper this right here. Okay. And so here n equals 2, and this is your principal quantum number. This represents L, your angular momentum number. And so we have P, and so this is 1, right? And then we know from here that our options would be for n sub L, our options are -1, 0, and 1. Alright? And so when we do these last 5 electrons, remember it's going to be up, 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 and then down and down. And where you put this last electron determines the orbital right here. So you put this last electron in here, and so n sub L is going to equal 0. Right? And because this last electron has a downward arrow, your spin number is -1/2. Okay? Now you may watch some videos where someone does something like this, where they start doing down, right? And then they draw them up. And this is why I said it's easier to do the convention that's up. And let's say you did this exact problem, and this last electron you put is up. Your spin number could also be +1/2. And it's like, well, why would it work that way? The main thing is that you wouldn't write it this way, right? You would go, if you started off going down, 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 right? You wouldn't have this, right? Because we can't have the same We cannot have the same spin numbers. And so as long as you draw it in such a way where the spin numbers are different, it is fine how you denote the spin, okay? But this is definitely wrong. Whoops. Well, I'll just erase it. I meant to put an X over it, but that is definitely wrong. And so if you go through some tutorial videos, I just want to point out, as long as those two spins are different within the same orbital, and that's how you're drawing it out, and you get a different spin number, that is fine. But also for consistency, it might just be easier to just draw it up in the beginning and go through and then put the down arrows after you fill up those after you put one in each orbital, okay? And so this would be your quantum numbers for where the last of the electron configuration is 2p5. Okay? And so pause the video and try finding the quantum numbers for 3d7. Okay? And so I'm assuming you've tried it. So n equals 3, right? Because that comes from here. And let's write our this denotes L. And you'll notice I said up here that L could be these, right? But this was just for you to understand how we're building up from N to L to M sub L. It's really these last ones. Right? I was just trying to explain that it contains 0, 1, 2, and 3, but when we're looking at that last electron, remember we said the last of the electron configuration, right? We are looking at that last shell, and so even though it contains all of these, when we're talking about that last electron and where it goes, we're talking about the highest number when it comes to N sub L, and that's why you write it here like that. And so all you have to do is know that it starts with 0, know it's SPD and F, and go up from there when you write it on your side of the side of your paper. And again, there are formulas for this. I don't like using formulas, I like using reasoning. So this is the only thing you would really have to memorize when you use like this reasoning method. And so I just wanted to point that out real quick. And so for here, right, we're at the D level, so D L equals 2, right? And for M sub L, our options are -2, -1, 0, 1, and 2. Okay, and so we have 7 electrons we're trying to place. So 1, 2, 3, 4, 5, 6, 7. Okay, and this is where you want to look at where that last electron is that you put, right? And so now we know that ML equals -1, and that our spin number is -1/2 because it's going downwards, right? And so you might ask, well, it could also be +1/2 if I draw it the other way. So how would I test you on this? How I might test you on this is I might say, true or false, downward spin equals +1/2. And that would be very much false. So very much false, because +1/2 is an upward spin, and -1/2 is your downward spin. Okay, so I'm going to leave this here for now because this was quite enough for one lecture. And so the practice that I've posted under Module 3, or if you're joining me on YouTube, under the Dropbox link, there are some practice problems for quantum numbers. And remember, with the answer key, if they come up with a different spin, that's fine. Okay, as long as you don't assign 2 numbers to the same orbital. That also might be another true-false question. Wink, wink, nudge, nudge.